You ever wonder why your ears pop when you dive deep into a pool? Or, how one of those tiny hydraulic jacks can lift an entire car? And what about a massive steel ship? How on earth does that float? Well, believe it or not, the answer to all of these questions is the same. It's a science called hydrostatics, and we're going to break it all down right now. Let's dive in.
All right, here's the plan. We're going to start with the basics. What even is hydrostatics? Then we'll get into pressure and this thing called Pascal's law. After that, we'll see why pressure changes with depth, how we actually measure it all, and finally, we'll uncover the secret of buoyancy. It's all going to build on itself, nice and simple.
Okay, section 1. Let's start right at the beginning and get our foundation solid. What exactly are we talking about when we say hydrostatics?
Yeah, let's go back to that ear-popping thing. That feeling, that pressure building up as you go deeper in a pool, that's not just some weird sensation. That's literally the core principle of hydrostatics in action, and we're going to figure out exactly what's causing it.
So what does hydrostatics actually mean? It's really simple. It's the study of fluids that aren't moving. They're just still, in equilibrium. So think of water in a glass, not a flowing river. And this stillness is super important because it means we only have to worry about two main forces. You've got gravity pulling everything down, and you've got pressure pushing from all sides. That's it. No complicated shear forces, just pressure and gravity.
Okay, so we've got our two main players, gravity and pressure. But let's be honest, the real star of the show here, the one that does all the interesting stuff, is definitely pressure.
So what is pressure, really? At its most basic, it's just how concentrated a force is. It's the force you're pushing with, divided by the area you're pushing on. Think about it. A thumbtack goes into a wall easily, right? Same force from your thumb, tiny area, that's high pressure. But if you tried to push the flat end of a hammer into the wall with that same force, not so much. Same force, huge area, that's low pressure. It's all about how spread out that force is.
And let's look at a real example of this. If you put a 500 Newton weight, which is, roughly 110 pounds, on a piston that's only about the size of a postage stamp, you get a whopping 200,000 pascals of pressure. That is a ton of pressure. In fact, it's about double the normal air pressure that's all around us right now. And it's all because that entire weight is focused on one tiny little spot.
This whole idea leads us to a really elegant, kind of beautiful concept in physics called Pascal's law. And what it says is this: if you're at any single point inside a fluid, the pressure is the same in every single direction. It's pushing up, down, left, right, diagonally, all with the exact same force. Pressure isn't a one-way street, it's an all-encompassing squeeze. Okay, hold on. If pressure is the same in all directions at one spot, then why does it change when we go deeper? Why do our ears pop? Well, that's the big question, and that's exactly what we're going to tackle next.
Let's just imagine for a second a vertical column of water, just sitting there. Simple enough, right? So what's happening to it? Well, gravity is pulling the whole thing down. That's its weight. For that column to just stay put and not fall, something has to be pushing up from the bottom to balance it out. And what's pushing up? It's the pressure from the water underneath. And that upward pressure has to be strong enough to hold up the weight of all the water stacked on top of it. That's the key right there.
And this idea gives us probably the most important equation in all of hydrostatics. Pressure equals rho g h. Now, don't let the letters scare you. Rho is just the fluid's density, how heavy it is. G is gravity, which is pretty much constant, and h is the depth. So what does this tell us? It's simple. The deeper you go, the bigger h gets, and the higher the pressure becomes. It's a straight line. More depth, more pressure, period. And here's a really cool consequence of that equation. The pressure only depends on how deep you are, not on the shape of the container. You could have a huge lake or a skinny little tube. If you're at the same depth in the water, the pressure is exactly the same. It's kind of counterintuitive, but it's true.
All right, so we've got the theory down cold. But how do we actually measure this invisible force? Let's take a look at some of the clever tools we use to do just that.
Okay, so we've got a few key instruments. The simplest is a piezometer. It's basically just a straw. You stick it in, and the pressure pushes the fluid up the tube. The higher it goes, the more pressure there is. Then you have the U-tube manometer, which is great for comparing the pressure between two different points. And a barometer? Well, that's just a special kind of manometer that's designed to do one thing: measure the pressure of the entire ocean of air we're living at the bottom of, our atmosphere. And now we get to the really cool part. This is where everything we've just learned about pressure and depth comes together to explain something that feels almost like magic: buoyancy, the force that makes things float.
So check this out. This is the big reveal. Buoyancy isn't some strange, separate force. It comes directly from what we already know. Pressure increases with depth. Think about any object underwater: a ball, a submarine, whatever. The bottom of that object is deeper than the top of it, right? That means the pressure pushing up on the bottom is always going to be greater than the pressure pushing down on the top. And that difference creates a net upward force. That's buoyancy.
So the next logical question is, how strong is that upward push? Well, it's a beautifully simple answer. The buoyant force is exactly equal to the weight of the fluid the object displaces, the water it pushes out of the way. That's the famous Archimedes principle. So the bigger the object, the more water it displaces, and the stronger that upward buoyant force is.
But just floating isn't enough, right? You also have to float without tipping over. That's where stability comes in. Every floating object has two important points: its center of gravity, which is where its own weight effectively pulls down, and its center of buoyancy, which is where the upward force pushes from. To be stable, you want that center of buoyancy to be above the center of gravity. That way, if the object starts to tip, those two forces work together to pull it right back upright.
Whew. Okay, we've gone through a lot, so let's take a second and just boil it all down to the absolute key takeaways.
So if you're going to remember anything, remember these three equations. First, you've got basic pressure, P equals F over A. That's just force spread over an area. Then you have hydrostatic pressure, P equals rho GH. That's the one that tells us pressure gets stronger the deeper you go. And finally, the buoyancy force, FB equals rho GV. That upward push is equal to the weight of the fluid you move out of the way. These three ideas right here are the foundation of hydrostatics.
So, let's circle all the way back to that big question from the beginning. How does a massive ship made of thousands of tons of steel actually float? I mean, a block of steel sinks like a rock, right? Well, the secret isn't what it's made of, it's the shape. A ship's giant hollow hull pushes a truly massive amount of water out of the way. And as we just learned, the buoyant force pushing up is equal to the weight of all that displaced water. The ship floats simply because its shape makes the upward push of the water stronger than the downward pull of its own weight. Pretty cool, huh? Something to think about next time you see one. Thanks for watching.